Hi, everyone. Thanks for joining us today for another session of EI Live K-12. My name is Cassie, and I'm going to be helping facilitate the session today. So for those of you who are joining us for the first time, we are the Earth Institute has now integrated into the Columbia Climate School, which is the first new school at Columbia University in over 25 years. And we're really excited about the opportunity for this new school, and the idea is for the university to draw on our collective strengths in the area of studying our Earth and Earth sciences and geosciences, and more broadly climate change and sustainability. And the Climate School is a hub for existing activities and world-class research centers, as well as programs. And so that includes the Earth Institute, which also includes the Lamont-Doherty Earth Observatory, which is a critical part of our research arm. And today we have Cari Leland from Lamont, and she also is affiliated with William Patterson University. And so she's going to be talking to you about tree rings, which is always one of my favorite topics for EI Live K-12, because I think it's so understudied and underutilized, and I love it every time to have Cari join us. During the session today, we're going to be using the Q&A box and not the chat box, and not the raise hand function. So if you do have questions that come up throughout the session, feel free to type it into the Q&A box. We also have a guest coming later on from NASA GIST to share some resources that NASA has with respect that's connected to the topic of tree rings. And what we're hoping to do with our EI Live 12 sessions, as always, is to bring our science to you, our audience here. We have many sessions left for this semester, and if you have any questions about what's left, feel free to contact me. You have my email address from receiving the reminders for this particular session. We do record everything. We'll share the recording likely this week, if not, then early next week. And all of these are archived on our website for you to access in the future. So Cari, if you want to take it away whenever you're ready, you can go ahead.
Great. Hello, everyone, and thank you so much, Cassie, for that introduction. And thank you, everyone, for being here today. It's always a pleasure to talk with students and families and educators about tree rings, because, as Cassie mentioned, tree rings are so fascinating and very accessible. So I've been doing tree ring research for about 15 years now. I started doing this research as a college student at West Virginia University, and I've been doing it ever since. So a lot of my research has focused on using tree rings to understand climate over the last 2,000 years. But more recently, I've become interested in this intersection between tree rings, archaeology, and history. And there are a lot of scientists working at this intersection and a lot of really interesting projects that are going on. So I'm really excited today to talk with you all about some of these interesting projects, and we will be solving mysteries of the past together. So yes, if you have any questions, as Cassie mentioned, feel free to make note of them, and then I'll be sure also to leave plenty of time at the end to answer those questions. Okay. And I just wanted to confirm, can everybody see my presentation?
I can, Cari, yes. And I think we have a question about not seeing the small speaker. Why don't you go ahead and let me try to resolve this, but I can see it just fine.
Okay, all right, sounds good. Great. So yeah, to get started, I think it's really important to note that every tree has an important story to tell. Every tree that you've encountered and seen in your life. So it doesn't matter if a tree is 2 years old or 2,000 years old. Every tree, as it's existing and growing in its environment, it is slowly recording information about the environment surrounding it all over or all during its lifetime. So because every tree has a story to tell, that means every piece of wood also has a story to tell. So it could be an old log in your backyard, or it could even be a piece of wood from your kitchen cabinet. That piece of wood was once from a living tree, and so there's a lot of interesting information in that wood. So it is our job as tree ring scientists to learn more about the history of those pieces of wood and to retell those stories. So what kind of information can we get from wooden structures or wooden objects? So you can pretend, for example, that you're out in the forest with your friends and maybe you stumble across a really old, mysterious log cabin. And if you wanted to, you could take a piece of wood from that cabin and you could analyze the wood and figure out when that cabin was constructed. Or you could be out diving in the ocean and you come across some mysterious wood from a shipwreck, and you can take up all of that wood and you can reconstruct the ship, and then you can analyze the wood and you can figure out where that ship was constructed. Or you could go to an art museum or an archaeological site and find a wooden structure, and by analyzing the wood you can figure out the origin of that structure. Or even musical instruments, many of them are made out of wood. So you could take a violin or a cello and you could look at the wood, figure out when and where that instrument was made, and potentially who made that instrument. So there's a lot of valuable information stored in wood, and we can uncover all of these stories simply by studying the tree rings that are within the wood. So some of you may be new to tree ring science, and the formal word for tree ring science, or the formal term, is dendrochronology, and that comes from the Greek dendron being tree, and chronology is the study of time. So essentially, we're looking at how trees are growing over time. And many of you have probably seen a stump out in the woods, and you might have noticed a collection of rings on the inside of a tree. So this is what dendrochronologists like to study. So what are these tree rings? Well, like us, trees will get taller as they age. Of course, we plateau at a certain point, but trees will continue to add vertical growth as they get older. And in addition to that vertical growth, trees will also get wider every year. So they will put on a new ring of growth every year. And you can get a pattern like you see here in the top right. Once again, we're looking at the inside of a tree, so looking at the stem. And yes, many trees, not all trees, but many trees in the world will produce a growth ring every single year. So in theory, you can count the rings to figure out how old a tree is. It ends up being a little bit more complicated, but that's the basic idea. And this is how you can interpret those rings. So on the inside of a tree, that is the year the tree was born, or that's the oldest year, the year that the tree germinated. And then it will add a new ring on the outside every year until the ring just behind the bark. This is the current year of growth. So if I looked at the rings of a tree in my backyard in the spring when trees are starting to grow again, that outer ring just below the bark will be the year 2022. And now we can zoom in and look at some of the features of the tree rings. So, you can take note of different features you see on this zoomed up image, and tree ring scientists spend a lot of time at the microscope looking at these details of tree rings. And some of us even look at high resolution images like you see here to look at these details as well. So what I noticed when I first look at this image is I see, first of all, the individual rings. So each tree ring, you can see there's a light part and then there's a dark boundary. So this is 1 year worth of growth. And within the individual ring, you might see these little tiny circles. And these circles are what we call cells. And basically, they just carry water from the roots of the trees all the way up to the top of the tree, to the leaves, where the tree can photosynthesize. And that's what allows the trees to grow. Of course, trees love to have lots of water. And so those are the individual cells. And now you also might notice when looking at the tree rings that there's a lot of variation in the size of the rings. So some of the rings are very wide, such as the one here on the left, and other rings are very small and narrow, such as the ring shown on the right. And some of you may have learned in school or in a program what causes this variation in the size of tree rings from year to year. And it turns out it's very complicated. In tree ring, scientists spend a lot of time trying to figure out what is causing that variation in the size of rings. But generally speaking, it is related to the environment from year to year. So for example, if a tree is really happy one year because there's a lot of rain, the tree has a lot of water, a lot of nutrients, a lot of sunlight, that tree, since they're so happy, it's going to grow a lot and it's going to produce a very large ring. If in the next year it's really dry, maybe there's not a lot of rain, the tree generally is not happy, then the tree will produce a small ring. So this is how we're able to look at the relationship between the size of the tree rings and changes in climate. And that is probably one of the important applications of tree ring science. It's for understanding how climate has changed in the past. But we can also study tree rings to understand something about the ecology of the past. So we can look at forest fires, for example, or past wind events or hurricanes. And of course, the topic of today's talk, tree rings are also important in archaeology. And it turns out that the variation that you saw of the wide and the narrow rings, that variation is very important for us to be able to figure out the history of old pieces of wood, wooden structures or wooden artifacts. And this image right here is a classic image in the field of dendrochronology, because it really nicely explains how we can use the patterns of tree rings to figure out the age of old structures. And this is how it works. So we can go back to that previous example where you're in the woods and you stumble across a mysterious log cabin. And let's say you tell your friends that you can look at a piece of wood from that log cabin and estimate the age of the cabin. So this is how you would do that. First, you would collect a sample from a living tree in that forest. So that's like example A here. And this is looking at the tree ring patterns of that living tree. So some years are wide and some years are narrow. And keep in mind that the inside of the tree, that's the oldest year when the tree was born. And the outside ring, this is the current year. So this tree was about 50 years old in this example. So now you have a nice pattern of growth from that living tree. Now you find a dead tree in that forest and you want to figure out, when did that tree die? So that's like example B. So once again, you can look at the patterns of ring widths through time, and you can match it up with the living tree. And what you might notice is that this is just like a giant puzzle. You can simply match the size of the rings through time. And once you have them matching up nicely, you can look at the outer ring of that dead tree and figure out the year that that particular tree died. And now we can take that even a step farther. And let's say you finally take a piece of wood from that log cabin. And you can do something like you had done with the dead tree. You can look at the sample. You can look at the patterns of rings through time. And once again, you're going to, like a puzzle, you're going to match this up with the other tree samples. And once you do that, you look at the last ring of that sample, and that will be the year that that tree was cut down in order to produce wood for the structure that you're looking at. So this is how we can estimate the age of historical structures. And people have been doing this for over 100 years at this point. So this is a very well-known method in dendrochronology, and it's called cross-dating. And there's a bonus to all of this because not only can you figure out how old that wood is from the structure, but you can also figure out where that wood came from. So in our example, if the ring width patterns from your log cabin match the ring patterns from trees in the local area, then you can feel confident that the wood just came from the neighboring forest. If, however, the patterns of rings don't match those trees and they match trees, let's say in New Jersey, 20 miles away, then you can feel confident that the wood from that structure actually came from New Jersey. So the pattern of ring widths is kind of like a barcode, and it helps us both date samples and also figure out where the wood came from. But there's a very important caveat which I want to note before we continue, and that is that you need to have enough tree rings in order to successfully do this kind of analysis. So if you give me a sample with only 5 tree rings, I don't have a lot of information to be able to cross-date that sample with other trees. So if you give me a sample with 150 or 200 tree rings, then there's a higher likelihood of being able to date that particular sample. All right, so now that you understand the general process of dating historical structures, I'm going to provide some interesting examples. And I can't talk about dendroarchaeology without talking about all of the amazing work that has been done in the southwestern United States. And this is actually the birthplace of dendroarchaeology. And scientists at the University of Arizona in Tucson, there's a very big tree ring lab there. They've been working on archaeological structures in the southwestern US for over 100 years at this point. And if you were to visit the lab, you would see that they have thousands upon thousands of tree ring samples from various archaeological sites in the region. And many of those samples are from the great houses of the ancestral Puebloans. And these are really remarkable structures that were constructed and inhabited from about 850 to 1140 CE. And a very famous great house is Pueblo Bonito, and this is in northern New Mexico. And I'm showing pictures of that site here. I think it's about 3 acres in size. And if you look inside the structure, there are some wooden timbers. And so timbers like this have been analyzed over decades at this point to understand the construction history of this site, which was very culturally important for the ancestral Puebloans. So there's a lot of really fascinating history here that has been figured out through tree ring analysis. And more recently, scientists have been looking at the tree ring patterns from sites like this to figure out where the wood came from. And in many cases, like here in Pueblo Bonito, a lot of the wood in some periods of time came from sites as far as 75 kilometers away in distant mountains. So it's really amazing how much information we can learn from the tree rings and these timbers. We can learn about when structures were built and also where the wood came from to build these really remarkable structures. And there are so many amazing dendroarchaeological projects that I could discuss. If I had time, I could go on for days about this. But for the sake of time today, I'm now going to focus on New York City because New York City is near and dear to my heart, and the tree ring lab at Lamont-Doherty Earth Observatory has worked on a lot of really interesting projects in New York City and also in the surrounding region, especially in the Hudson Valley. So I'm going to talk about one project that happened back in 2010, which is really interesting for a lot of people. And this was the World Trade Center ship. So in 2010, excavators were working at the World Trade Center site in Lower Manhattan. And they came across the bones of a mysterious ship underground. And this ship, which you can see here, this is the hull that you're looking at. So there are a bunch of timbers, and nobody knew the origin of this ship, but people became very, very curious about it. And here are some pictures of the excavators pulling the ship from below ground. And I think it was about 20 feet below the surface of the ground. So it was buried very deep. And your first question might be, why was there a ship below ground? And that's a very good question. It's really interesting because a lot of Lower Manhattan is not actually like natural ground. So centuries ago, people wanted to extend the island. So they put a bunch of fill material like rocks and dirt, garbage, and even old ships in order to physically build land so that they could build on top of it. So archaeologists have actually been studying Lower Manhattan for a long time because there are literally layers of history of when the island was built up. So this is one hypothesis as to how the ship kind of got here to begin with. It was just that process of creating land in Lower Manhattan. And so they pulled up this ship, and then they contacted scientists at the tree ring lab at Lamont, and all of the names here below, everyone was involved in this really exciting project soon after this discovery in 2010. So they took some samples from this ship and brought it back to the tree ring lab for analysis. And even before analyzing the tree rings, the scientists noted something that was very interesting. They found that the ship was made mostly of oak trees, which is a particular type of tree. And specifically, it was from the white oak group. And they also found that the keel of the ship was made of hickory, and they think that was shagbark hickory. So that's another species of tree. And with this discovery, they were able to kind of hypothesize as to where this ship might have come from. Different kinds of trees have different distributions across the world. So white oak tends to be very broadly distributed. You can find it in a lot of places, but hickory is a little bit more narrow in terms of its distribution. So the fact that the scientists found the ship was made of oak and hickory allowed them to hypothesize that the ship was constructed in, the wood from the ship was taken from the Eastern United States. So that was already a really great hypothesis to start out with. And then they were able to start with the tree ring analysis to learn more specifics about the ship. So what they did is they measured every single ring. They looked underneath the microscope and they measured the rings of all of the samples they collected. And then they had a nice series of measurements of the different sizes of the rings. And they compared this ring pattern to tree ring data from throughout the Eastern United States. And what they found was that the tree ring data from the World Trade Center ship very closely matched the patterns of tree rings in the Philadelphia region. And that is shown here in this image. So you don't have to get too caught up on the details here on this image, but what we're looking at is time. So the years 1500 all the way to 1800. And then the tree ring pattern is for the World Trade Center ship is represented by this squiggly black line. And the big values, those are years in which the rings were big. And the small values, these are years in which the rings were small. So you can see the World Trade Center ship growth pattern here. And then this was compared with the Philadelphia oak tree ring data, which is shown in gray. And what you might notice is that there is a very strong relationship between the two. The squiggles kind of match each other. So that's a really great sign. That means that the World Trade Center ship, the wood from that ship likely came from the greater Philadelphia region. Mystery solved. And in addition to that, the last ring that they discovered from the World Trade Center ship was 1773. So that means that the wood for the ship was cut around 1773. And so then they had a date as well as a location for the origin of this ship, which is really, really exciting. And I wanted to also highlight another interesting finding. And it just goes to show that science is very collaborative. So scientists that focus on different specialties like to work together to paint a bigger picture of whatever they're studying. So in this case, they spoke with someone who was an expert in shipworms. And it turns out that some of the wood from the ship had damage from shipworms. And that expert looked at the wood, and based on the damage, they concluded that it was from shipworms in the Caribbean. So with this extra piece of information, not only did they figure out where the ship came from and roughly when it was constructed, but they could also deduce that the ship spent some time in the Caribbean during its lifetime. So it's really interesting, all of the information that you can get just from really a few pieces of wood from a structure. Okay, so yeah, that was around 2010 when that ship was excavated. And now we're going to move forward in time. This was, I believe, 2019. We had a really fun opportunity to work at the terminal warehouse, which is located in Chelsea in New York City. And my colleague, Makunz Palatrao, took this picture. And here you can pretend like you're walking south on the High Line. So the Hudson River is to the right here. And for those of you from New York City, maybe you've seen this building. It's a gargantuan building, so it's really hard to miss. And yes, this is the terminal warehouse, which has a very interesting history. It was built in the 1890s, and it is a true symbol of the Gilded Age of New York City. So the Gilded Age started in the late 1800s, and this was a period of glitz and glamour and really rapid expansion and development of New York City. And this structure, the terminal warehouse, was very important. It was connected directly to the rail lines. So a lot of goods moved in and out of this warehouse. And it was also initially designed for storage. So storage of all sorts of goods, including cold refrigerated goods. So it's a very fascinating building, and it had an interesting evolution through time. And people from the terminal warehouse were curious about the history of some of the timbers from the original construction. And so they reached out to some of us at the Lamont-Doherty Tree Ring Lab to uncover the history of this building. So in this case, it was a little different because they knew the building was from the 1890s, but they wanted to know about the origin of the timbers that were in the building. So we went to do field work in the building, and it was really exciting because they had these amazing wooden beams, but also in their basement, which was a really cool place. Not many people get to visit the terminal warehouse basement. they had stored a bunch of timbers from the original construction that had been recently taken down. And for a lot of people, this may not look very exciting. It's just a bunch of wood stacked on top of one another. But for tree ring scientists, we all got really excited. Our eyes almost popped out of our heads because we looked at the timbers and we saw a bunch of tiny, tiny little rings. So to us, that was really exciting because it meant that this wood was really old. These are probably old growth trees from who knows where, right? That was why we were there. We wanted to look at these tree ring samples and figure out where this wood came from to help solve the mystery of the terminal warehouse. So with the chainsaw, we collected a bunch of these samples and we brought them back to the lab and sanded them up. So here are some examples shown on the left. These are the samples that looked nice. So you can see all of the tiny little rings, right? Really exciting. Some of these samples have 200 plus rings on them. And we soon learned that these timbers were made of longleaf pine. And longleaf pine is a very special tree. It grows only in the southeastern United States. And there's a map shown on the right with the green boundary. So this is the distribution of longleaf pine. And this tree used to be all over the place. It was very common in that region. But unfortunately, a lot of these forests were completely cut down in the late 1800s and early 1900s because the timber industry was just going crazy. So there's a lot of new technology to help the timber industry break down more forests. And then also the railroad system had expanded drastically. So these intact forests that were once so beautiful and consisted of a lot of old trees were suddenly cut down, which was very, very sad. And to this day, I think they estimate that less than 5% of those longleaf forests are still intact. And they're very unique and cool ecosystems as well. So anyway, it was a big loss. And a lot of these longleaf trees, the timber, they went to developing cities like New York City, Boston, and other large cities. So when we found that the terminal warehouse timbers, many of them were made of longleaf pine, we weren't particularly surprised, given that the terminal warehouse was built in the 1890s. But anyway, we did our tree ring analysis, and using the same method that I told you about for the World Trade Center, we compared our tree ring patterns from these samples with longleaf pine tree ring other sites in the southeastern United States. And we found that these timbers came from this region here, the border between Alabama and Georgia. So we don't know exactly where the trees came from in this region, but the tree ring samples match very well tree ring data that exists here. So that was really exciting for us to learn a little bit more about the history of terminal warehouse. And it got us really excited to learn more about the history of other New York City buildings as well. And so that's where we currently are. And we actually have other projects going on that are very, very exciting for us. And next, we've been working on demolition sites, and I'm working with my good colleagues and friends, especially Makun Palat-Rao and Milagros Rodriguez-Caton, as well as Ed Cook and other collaborators at Lamont. And we've been working with Alan Solomon, who is a co-owner of Sawkill Lumber in Brooklyn. And Alan goes to a lot of these demolition sites and salvages wood and repurposes them. So he's been an amazing person to work and learn from. And it's just amazing because a lot of these demolition sites in New York City have an incredible amount of wood in them. And demolitions are occurring all the time in the city. oftentimes really old buildings are being demolished, and the wood in these buildings, it's extremely valuable. They're valuable because, of course, first of all, they can be repurposed, and sadly, a lot of the wood is sent straight to the landfill, which is a total waste. But a lot of this wood for sure can be repurposed and made into other things. But also, as we've talked about today, this wood has a lot of very interesting information about the past. So not only can we learn about the history of these old New York City buildings and the history of the logging industry by analyzing samples from these demolition sites, but also we can use these tree ring data for other scientific questions as well. We know that the tree rings tell us about past climate and past ecology. So our hope is to collect and save as many of these timbers from demolition sites as possible so that we have all of that information that can be used for better understanding history, climate, and ecology of the past. And on top of that, a lot of the timbers from these old buildings are from really old trees. And so it's really hard to find old growth forests these days. So to have these really long records of growth from these demolition sites, it's even more exciting because that means we can extend our tree ring data collections even further back in time. So there's a lot of potential in studying timbers from these demolition sites, and we're looking forward to working on more of these sites in the future. Okay, so hopefully this talk inspired you to think about some tree ring mysteries that you would like to solve. And of course, I'm happy to answer any questions that you might have. And and thank you so much for listening.
Great, thanks, Cari. So we have a comment and a question in the Q&A box. If you want to tackle those, or we can choose to answer those live as well. But if I could get you to stop sharing your screen, and we'll have Rosalba share her resources. And then Cari, what you can choose to do is either answer live or you can type the questions as Rosalba is sharing her resources. Rosalba, if you're here and you'd like to unmute yourself and share your slides. So Rosalba, for everybody who's joined us a bit later, is from NASA GISS, and she's here to share some NASA relevant resources about tree rings and things that are relevant to the topic. So Rosalba, you can go ahead.
Thank you, Cassie. Can you hear me?
Yes.
Is my screen also sharing? Okay.
Sorry, we're not seeing your shared screen.
Okay, let me try. How about now?
Yes, go ahead.
Great. Awesome. Thank you so much. So I put some links on the chat about some resources that I would like to share with you. Like Cari said, tree rings can also help us learn about climate. So today I want to share about some resources that can help you learn about that aspect of tree rings. So I would like to share about climate kits, also the NASA Earth Observatory paleoclimatology webpage, and also a platform that is called My NASA Data. So first, Climate Kits is a pretty fun website. It has games, hands-on activities, interviews to scientists, videos, and so you can learn about a lot about earth science and climate change. The link that I shared with you in the chat is specifically a section that talks about tree rings and how we can learn about past climate from them. And then the next resource is the NASA Earth Observatory webpage. So here you can learn about how many elements of Earth can help you understand past climate. So like coral and cave rocks and ice cores, and of course also tree rings. So again, the link that I shared is specifically the section about tree rings, but of course We're welcome to explore how many other elements of Earth can help us understand our past climate. And last but not least, if there are any teachers on this call, there is this platform called My NASA Data. So of course, as you know, NASA has a lot of data related to Earth that comes from satellites, but it can be tricky to access that data or to interpret that data. And so this platform helps students and teachers access the data easily. And so the link that I shared is for an activity or actually a lesson plan that lets students compare authentic precipitation data from satellites to the width of 3 rings so that they can determine the similarities and the differences in the precipitation patterns. So I think it's a very, very cool activity. I hope that you check it out. And that's it. That's it for me today. Thank you.
Great, thanks, Rosaba.